Hi, I'm Kevin Dorma. The traditional way, and the simplest way to heat our homes in Alberta is with a natural gas-fired furnace. But that's not the only way. We could also use an air source heat pump, which is essentially a refrigeration unit that tries to cool off the outside by pushing heat into the house. Now, heat pumps are fairly common in areas that don't have extensive natural gas distributions and places that are a bit warmer than Alberta. Now, heat pumps have been traditionally limited to areas with fairly mild winters, like over about 0 Celsius, and this is to prevent frost buildup on the unit. However, there's been some advances in defrosting techniques, and now we have cold climate air source heat pumps. And these have been used fairly successfully down to about -25. And you can find cold climate air source heat pumps in Manitoba, and it gets pretty darn cold there. Now, the objective of this study is to determine if a cold climate air source heat pump is efficient in Calgary in terms of cost and in terms of CO2 emissions. Now, I'm not just going to show you the answer. I'm going to go through the Python code to actually walk through all of the steps that are needed to analyze this. And it's going to take a bit of work. This is a little bit like shaving a yak. Let's dive into it. Okay, so here's my Jupyter Notebook. I'm using Python, and this is where all the calculations are done. And I'll walk through all of the things that we need. Okay, so the first thing that we need is some data for the coefficient of performance for an air source heat pump. COP is the ratio of the amount of heat that we get into the house compared to the amount of heat that we push into the, or supply to the heat pump by or with electricity. So here's one data source from a guy by the name of Shin. And the data that looks not too bad is the black stuff. And we could digitize a couple of points here and get a decent line. You know, the COP is a little bit on the low side. Kind of tapers off at 10 Fahrenheit. But then we can pick it up at the purple lines, which looks about the same performance. And it goes all the way down to about -10 Fahrenheit. So that's one piece of data. We could also use the green dots, and we've got, looks like, a higher coefficient of performance, but the data ends at about 13 Fahrenheit, so I'm not sure if this is a really good cold climate unit. So I got two pieces of data, and I'm not sure about either one. Now, another piece of data that I found is for a more experimental heat pump, and this was tested in Alaska. So the data is from Alaska. And this has some COP data that goes all the way down, it looks like about -13 Fahrenheit. So what we can do is we can take these graphs, digitize them, get a few points, and then plot a couple of curves. And I did just that. So there's the curves for the COP as a function of temperature. And I converted this to Celsius because I like Celsius. Okay. And here, the research one has a COP of 2 for the low temperatures, and it creeps up. Now, the performance isn't quite as high as one piece of data that we looked at, but because I trust this data a bit more, I'm going to use it. I suspect the COP might be we might be able to find a heat pump with better performance than this red line, but we're going to use the red line. So that's the data that we're going to use. So now we have the performance of a heat pump as a function of the ambient temperature. Great. That's nice, but the ambient temperature changes during the heating season. So now what do we do? Okay. Well, we also need to know how much heat is needed to heat my house. So this is the gas bill for my house. And I just scanned it, plopped it here. So in the winter, in the dead of winter, in the really cold months, oh gosh, it's about 28 gigajoules. That was a cold month. And we can also get the monthly temperature that corresponds with these months. Put them in a data frame, look at the data, and now we have a table with the amount of heat that we need for the house and the ambient temperature. And these are monthly average temperatures. I got those from Environment Canada. Okay, great. And we can plot a graph. And no surprise, it's fairly linear. As the temperature gets colder, the amount of heat that we need to keep our house warm is pretty linear. Okay, that's pretty good. Got that. But now we need to create a model. Okay. One of the things that I noticed on the data is that there's the heat that we need for the house drops off to with a constant value of about 2 gigajoules per month, even in the summer. And I think this is for hot water. So I'm going to imagine that I need a base load of 2 gigajoules a month, and I'll also imagine that the furnace efficiency is about 75%. So I just want the actual heat for the house, not the natural gas that I'm burning. So I need to do a bit of math, and I need to fit a curve to it. So there's some Python code for fitting a curve to it. And there's my curve. And this is now the model in terms of that expresses gigajoules per hour of heat required to the house as a function of outdoor temperature. Awesome. Got that. But that's for monthly averages, and we know that the ambient temperature changes from hour to hour. What do? Well, first we have to assume that our data or our correlation for heat required for the house that we got from the average monthly temperatures can be extrapolated to the extreme temperatures that we see on an hour-by-hour basis. That should be okay. But we need to get some hourly data for the ambient temperature, and that is a yak all to itself. Okay, we need to get some data. So hop over to Environment Canada. They've got lots of historical data for lots of weather stations, and here's the site, climate.weather.gc.ca, and chances are you can find a site close to you. So go to the site that you want, and we could just get, and I'll just pop onto that right now. And I can say, I'm waiting for this thing to refresh. And we could look for Calgary. And there's a bunch of things here for Calgary, but I want this one. And this is actually the one that I want. I want to go here. Come on. There we go. Okay. And so we could get some data for Calgary. And we could download a month worth of data at a time, but my goodness, that would be painful. We have a better way to do it. If we go up here into the HTML code for this page, we can find a very convenient string. There's a bunch of data for a bunch of information for what defines the data. The one we're interested in is right here. The station ID 27211. So we're going to copy that and we're going to paste it someplace. So we need that. Let's go back over to our Jupyter Notebook here. So this is the station ID number. We need that. And now we're going to use a little bit of code that the nice folks at Environment Canada provided that fetches whack loads of data from the command line. And I'm running a Mac, so it's kind of like using Linux. Okay, so I need this little bit of code. Most of this is provided by Environment Canada, and I just cleaned up the code a bit to make it easier to read. There's a station ID number right here, and this is the code that does all the grunt work. For every year in this sequence, 2006, to 2021. We want to go for each month in the sequence 1 through 12, and we're going to get a bunch of data, and this is the string that we want to execute. And station ID is here, here's the year, here's the month. So we take this bit of code, and we could copy it, we could paste it into a command line, which I won't do because it takes forever to run. And we get a whole bunch of files. Lots, like we get one file for every month. We got about 15 years worth of data, so that's about, 150 files. Okay. Now we want to combine all the files into one great big file. And so at the command line, we will concatenate all the files that start with en_climate.cv and put them into something called data.cv. That's great, but every file has a header. We need to strip that out. So now we can use the Linux or the Unix command grep and get rid of anything that contains a string that's in the header file. The header contains the word longitude. So run this command, and then we get rid of all the headers. We need one header though, because we need a header for our data set. So this little command, head -n1, says take the first line from one of our data files, and we'll call that header.csv. And that is actually not correct. That should be data2. Probably data.csv, not data2.csv. My apologies. And now concatenate the header with the bulk of the data table. So cat header.csv, data2.csv, Calgary weather2.csv, and voila, we finally have a whole bunch of hourly data for the city that we're interested in. And we might be able to do this all in Python, but I don't know how. I do this from the command line. Okay, so now we've got 12 years of hourly data. Now we need to do some processing with this. So we'll pull that into a data table. We'll take a look at the top couple of lines just to peek at the data, and the data looks pretty good. Every column, there's columns for longitude, latitude, station name, climate ID, year, month, day, time, and this is the one we want, temperature. We have to convert some of these columns into floating point numbers. Some of them have to be converted into integers. And this is just sort of the data mangling we need to go through. But the most important one here is we want to cut all of this data into a bunch of bins. We want a frequency distribution. So we're going to take all the data according to the real temperature, or the temperature in real, as a real number or floating point number, and cut that into 30 discrete bins. And we'll create a histogram. And there's our histogram. So the low temperature side is -32.5 to -30, and looks like in the past 15 years, we had that it got that cold a couple of times. We've got some fairly frequent temperatures in the -2 to 0 range, another peak in the 11 to 13.5 degree range, and then the temperature warms up and we get the odd hour where it's over 32 degrees. Okay, so now we have a histogram. Great. Oh, but we need the midpoint. We can't do math with ranges, we need actual numbers. So we need to calculate the midpoint temperature for each range. Well, that's pretty easy. There's a bit of code for it. There's a function called mid. Works fine. Okay. we've got 15 or so years of data. Now we can normalize the hours to get a decent statistical picture for how many hours we would expect in a typical year for each of these temperature bins. So we do a value count, we normalize it, and we multiply it by the number of hours per year. We'll take a look at the top couple of rows in this calculation, and it says for times where the temperature is about minus 31, there's about 7 hours per year where we see that. And we will see temperatures below minus 25 about 65 hours per year. Now it's time to start compiling some data for the task that we're doing. Okay, and we're going to compile this into a variable called home heat. So this is where I actually construct the data table. So the first column that we add will be ambient temperature. That's what we want, and that's in degrees Celsius. And then to that table, we're going to add the number of hours that we expect each of these temperature bins to have. So that's the next column that we have in our table. So now I've got a table with two columns. Temperature, the midpoint temperature on each bin, and the number of hours that we can statistically expect to see this per year. And I'm not showing the entire table because there's 30 rows in it. Well, that's great. But how much heat do we need for each of these temperature bins? Okay. To do that, we're going to take our correlation that we had for the heat rate that we need for our house as a function of ambient temperature. And we can apply this to every every row in our data table. So we can say the design heat rate is equal to a model prediction. Okay, so now we have a design heat rate, and this has units of gigajoules per hour. So when it is minus 31 outside, well, that's 7 hours per year, my house needs 47,321 kilojoules per hour of heat for that house to maintain that temperature. Well, that's nice, but I need the total amount of heat, the total kilojoules, not the kilojoules per hour associated with each of these bins. Well, that's actually fairly straightforward, because if I've got kilojoules per hour and I've got the number of hours, multiply them together, and I get the number of kilojoules of heat. So we just multiply the two columns together. Now I've got the amount of heat that I need for this minus 31 degrees Celsius bin. And we do that for all the bins. Okay. Well, that's heat for the house, but I need the electrical energy needed to move this heat from outside to inside. Well, the nice thing is we've got our graph of coefficient of performance. Now I can use that graph or the data on it with a lookup table. And I can use linear interpolation. There's a nice function for that in Python. So I can use a linear interpolation, and I can create another column. We'll call that coefficient of performance. I get the coefficient of performance for each of these temperature bins. And once I've got that, now I can determine the amount of energy that I need to move the amount of heat for each of these temperature bins. And that's just a simple bit of arithmetic. So for each temperature bin, I've got the coefficient of performance, and it's a low number for minus 31, and it's creeping up as we get warmer. And I calculate the amount of energy that's needed, the amount of electrical energy needed for each of these temperature bins. Okay, we're getting closer. But we need the cost of the electrical power, and we need the amount of natural gas that we would have to burn in a combined cycle gas turbine power plant to make the electricity that we're going to put into our heat pump. Okay, cost of energy. Okay, the first thing, not cost. First thing we need to look at is the amount of CO2. Now, by rights, we don't need to look at the amount of CO2 since we're comparing methane burning in a furnace to methane burning in a gas cycle, combined cycle gas turbine power plant. Methane is methane, so you don't have a difference in fuels, but it's very nice to use CO2 as a basis. Okay, so the heating value for natural gas is a touch over 55,000 kilojoules per kilogram. The methane intensity, the CO2 intensity for methane, it comes from the ratio of the molecular weights, because 1 mole of methane produces 1 mole of CO2. And then from that, we get the CO2 intensity for the fuel. And this is about 50 kilograms of CO2 per gigajoule of methane. And there's the number in kilograms of CO2 per kilojoule. We also need the amount of fuel, the mass of fuel that's needed to produce 1 kilojoule of electricity from a combined cycle plant. Now, the combined cycle gas turbine heat rate is 7,649 BTUs per kilowatt hour. I think this number comes from the US government source. I can find it. So we want to convert this into nice SI units. So we convert BTU into kilojoules and hours into seconds. And now we get the coefficient of performance in terms of kilojoules of heat that is moved, the kilojoules of fuel that is burned in a gas cycle, in a combined cycle gas turbine plant to produce 1 kilojoule of electrical energy. And the coefficient of performance for our gas furnace is 0.9, and that's just the efficiency of the furnace. Okay. Oh yeah, we need some gas prices. And I took this straight from my natural gas bill. So I just looked at the total that I spent in a month, subtracted off the fixed charges, and then I made sure that I included everything that was prorated by the gigajoules of gas being used, things like transmission charges. Okay, and also looked at electrical price, just for fun, and expressed this in dollars per gigajoule, just to make sure. Now, take a look at this. Fuel is about $8.80 per gigajoule. Electricity is a touch over $39 per gigajoule. Electricity is about 4.5 times more expensive than natural gas on an energy basis. And this difference reflects the efficiency in producing electricity from gas. Efficiency is about 40% at best from a combined cycle plant. And it also reflects the payment of the capital, the equipment that is needed to produce the power. This is why electricity is expensive, more expensive than natural gas. So since electricity is considerably more expensive than natural gas, I'll say things don't look too good for the financial justification for an air source heat pump in Calgary. And now we will take these economic values and CO2 values and energy values and plop those into our data table. So add some columns for the amount of gas fuel associated with driving the gas turbine, which produces electrical power, which spins our heat pump, the amount of fuel needed for our furnace, and the electrical and the utility cost for each of these. And conveniently, I will drop the rows that are 0 or where we don't need heat, because I'm going to do some math with those. So I'm just dropping some rows in our table. Okay, so there's the first couple of rows. Again, our table's getting pretty big. I think we're almost done with this yak. We've done a lot of work. I think we're almost finished. Now it's time to look at the answers. First, we're going to look at the amount of energy that is needed to keep our house warm and where the majority of our heat is used. The blue line is our furnace. And we have a peak around 0 Celsius. Most of the heat that we need for our furnace, or most of the heat needed to keep our house warm, is actually at fairly warm temperatures, say between about -8 Celsius and going up to maybe 3 degrees Celsius. That's because most of the hours for heating are in this range. Now, by comparison, most of the energy needed to drive that heat pump extends a little bit lower. It goes all the way down to about -15 or a touch lower. And this is because the heat pump is quite efficient at the nice warm temperatures of 0 degrees and becomes less effective as we get down lower in temperature. But we can see that driving the heat pump requires less energy, and this means lower CO2 emissions. But what about the cost? Okay, so here's the cost. The peak cost that we spend on fuel for the furnace is right at 0 degrees because we spend so many hours around that temperature. For the heat pump, it stretches out and drops down and is still high at the -15 temperature range. But notice that it's always more expensive to operate the heat pump than it is to operate the furnace. Always. And here it's useful to look at the total amount of energy that we use for heating the house. So this is the cumulative gigajoules of heat that we use, or gigajoules of energy, natural gas energy, that we use to either drive a heat pump through electricity or in a furnace directly. Now down at the low end, -30 degrees, there's no difference until we get up to around -15. The heat pump is a clear winner. The amount of energy that we need to keep our house warm with a heat pump is about 30% lower than the total amount of heat that we need to keep the house warm with using a natural gas-fired furnace. And we can look at cost. But this is where we see the opposite trend. The heat pump requires about 40% more money to purchase the utilities to keep our house warm than the simpler way of doing this with a natural gas-fired furnace. That was an awful lot of work to explain or to sort out if an air source heat pump makes sense in Calgary. And the answers that I got, I really didn't expect. I didn't expect an air source heat pump to even be a viable option in any sense of the word, either in fuel consumption or in cost, and I was quite surprised by the answer. So even though Alberta produces electricity by burning natural gas in a combined cycle plant, and Calgary winters are rather cold, using a cold climate air source heat pump should yield a savings of about 30% on CO2 emissions over the natural gas furnace. Now, I expect the natural gas furnace is still needed as backup for those infrequent hours where it's bitterly cold outside, but that's not too bad. However, financially, the gas furnace wins in Calgary in terms of utility cost. And this is, and as well, it's about 40% less expensive for utility cost. And as well, installing a gas furnace is less expensive than installing a heat pump. And these results depend on the ambient temperature. So we could do this for Edmonton, and we would end up going through the same steps again, but for a city that has colder winters than Calgary. So in Edmonton, I would expect the furnace to be a clear winner in terms of both CO2 emissions and fuel cost. But For people that are living a little bit further south in warmer cities, such as Lethbridge or Medicine Hat, they may find that a cold climate heat pump is attractive in terms of the cost effectiveness and offering a significant reduction in CO2 emissions. Happy yak shaving. Thanks very much. Bye-bye.